start with just a simple reminder of how to estimate things. So let's say we have this curve, it's a heavy black line, and so f of x is kind of like y, the dependent variable, versus x, the dependent one. And we have some position x sub I, so I is what we call an index, and we step forward by some small distance delta x, so to xi plus 1. And in that same time, the curve has increased in its value to some true f of xi plus 1. So if we just use, for example, a linear sort of estimation of where it should be, we have a little bit of an error. And so you can see that the smaller the delta x is, even a linear estimation can kind of work. But that's basically what we're doing. We're just doing very simple linear approximations, but keeping the delta x's really small. So on the right side, we add a xi minus 1. So we have a delta x behind and a delta x in front of our position of interest xi. So the curve goes through there still, and the true, let's say the tangent, is right at xi. But if we want to calculate the slope, or that tangent, we could go backwards, and that's not too bad, approximation, or forward, or we could do it by basically going from xi minus 1 through xi to xi plus 1, and that way actually we estimate it and right at xi, but we're doing it over a span of 2 delta x's. And so again, if delta x is small, this is a pretty good approximation, and that's called a centered difference. Okay, so given all of that setup, now let's just take our basic diffusion equation apart and turn it into a series of approximations. So the first thing we're going to do is use a forward difference in time to approximate the change in elevation with time. So dh dt is equal to the elevation at node I at time L plus 1 minus the elevation at that same node at time L, so that's just delta H, divided by the time over which that change occurred. So simple forward difference in time. Now the right side of the main diffusion equation, we can step back and say, well, it's really the difference in flux into and out of x sub I. So recall the continuity discussion. So here we just say qs out minus qs in. And so that's the transport rate k times the change in elevation from hi to hi plus 1, and all of this is at time L, divided by delta x. And then that's qs out. Qs in is just the change in elevation from hi minus 1 to hi divided by delta x. So then we can simplify, so we pull the k's to the left, and also in order to simplify, we have delta x squared as a constant, and then these elevations. So we take those two, equations 2 and 5, and plug them respectively into equation 1, and then we just want to simplify and rearrange to solve for the future elevation, hi L plus 1, as a function of all the current elevations. And so you can see also this k delta t over delta x squared we call lambda, and that's an important kind of collection of constants and also a measure of stability. So we'll see when we implement this in Excel that lambda has to stay below 0.5 for our simple implementation. So then this graphic just shows how we set the nodes up. We have the edge nodes where we can't really compute that center difference. We have to sort of tell it what's going on, that, for example, the elevation is fixed. So that's the white nodes at the left and right side of the model. And then the inner nodes, the black nodes, are the ones where we use that little equation and we calculate going along in I and forward in L. And here's just a zoom to show how that works, where we're going forward in time and then we go to the right in space, and so the circles show how we do the right side of the equation, and the x's show how we do the left side, the time difference.